Okay, so let's talk through this text on linear programming. And by the way, if you want to know where this comes from, it's from the National Council of Educational Research and Training from India. Indian education is very strong in applied mathematics. So this is a good reference, and you may find other references here on this page that are of interest to you. So let's go back and work through this. We start with a practical problem. By the way, RS means rupees, so you can think of this as dollars. Let's read this problem. A furniture dealer deals in only two items, tables and chairs. He has 50,000 rupees to invest and has storage space of at most 60 pieces of furniture. So he can only put 60 pieces of furniture in his storage. He can't have more than that as inventory. All right, a table costs 2,500 rupees, a chair costs 500 rupees. He estimates from the sale of one table he can make a profit of 250 rupees, and from the sale of one chair a profit of 75 rupees. He wants to know how many tables and chairs he should buy from the available money so as to maximize his total profit, assuming he can sell all the items which he buys. All right? So he has limitation in how much furniture he can store. He's got two different types of furniture with two different profits and two different costs. So I should say he has limitations both in his storage space and in his investment. Okay, so you have both limitations and benefits. All right, such types of problems which seek to maximize or to minimize the profit, or in other problems you might have the cost. This type of problem forms a general class called optimization problems. Right? So a special but very important class of optimization problems is linear programming problems. The above example is an example of linear programming, and we'll explain why it's called linear programming presently. So let's talk about some terminology. Now, if you think of the problem, what we're talking about is deciding upon the dealer's best strategy. Right? His strategy basically is how many chairs and how many tables he buys. So that's a strategic question. Now, there's certain conditions or limitations, or we call them constraints. Right, he has maximum 50,000 rupees investment and maximum storage space 60 pieces. So these are called constraints, and we'll be calling such limitations constraints throughout the course. We'll see many different types of constraints. These constraints are rather simple. Right. Now, if he bought tables and no chairs, he could buy 50,000 divided by 2,500. Why is that? Because this is the amount of money he has, and this is the amount of money per table. So he can't buy more than that, because if he did, he would spend more than 50,000 rupees. You can verify that 20 times 2,500 is 50,000. All right. Now we have to be careful here. Does he have enough storage space to store these tables? And the answer is yes, because he can store 60 pieces, and here in this case he would only buy 20 tables. So if he did buy 20 tables, he would get the profit per table, which is 250, times the number of tables. So profit is 5,000 rupees. Now on the other hand, he could buy only chairs and no tables. He has 50,000 rupees, so he could buy 50,000 divided by 500. Remember, 500 is the price of one chair. So he could buy 100 chairs, many more chairs. However, he has another limitation. He can only store 60 pieces. Therefore, he's forced to buy only 60 chairs. In this case, he would get 60 times 75, or 4,500 rupees. Right? So it seems that he should buy tables rather than chairs. But think about this. The chairs cost a lot more than tables. But they've got comparatively speaking, a larger profit. The profit is 75, which is about a quarter of 250, but the chairs cost much less than the tables. The chairs cost only 1/5 what a table costs. So it seems like you'd like to buy as many chairs as possible, but you're limited because you have limited storage. So how do you solve this problem? You've got conflicting requirements. So in this case, he buys a mixture, 10 tables and 50 chairs. Now what you have to make sure is that he can actually buy this many tables and this many chairs. 10 tables would be 10 times 2,500, which would be 25,000, and then 50 chairs would be 50 times 500, which is also 25,000. That makes 50,000 altogether. So it is possible for him to buy 10 tables and 50 chairs, and he has this amount of storage space. Now you can figure out what the profit would be. The profit from the tables would be the number of tables times the profit per table plus number of chairs times the profit per chair. You can work this out, 6250 rupees, which is more than the two cases we've seen so far. So it looks like you want some kind of mixed strategy to optimize, right? Now so far we've dealt with words. Let's see if we can formulate this mathematically. All right, so we have tables and chairs. We can identify these as variables. These are the things that we can choose. This is what we want to determine that determines our strategy. So we'll let X be the number of tables I buy, and let Y be the number of chairs that the dealer buys. So obviously they must be non-negative. You can't buy a negative number of tables or a negative number of chairs. So mathematically we need to include these two conditions, that X is greater than or equal to 0 and Y is greater than or equal to 0. Now we have two additional constraints. We noted that he can only buy a certain amount because he has a certain amount of money. So if he buys X tables and Y chairs, how much money does he spend? Well, X is the number of tables. You have to multiply X by the cost per table. So that's 2,500. So 2,500X is the total amount he spends on tables, plus the total amount he spends on chairs is going to be the cost per chair, which is 500, times the number of chairs, which is Y. So this quantity here on the left-hand side is the total amount of money he spends on tables and chairs. And we've been told that he only has 50,000 rupees. So this is a constraint, a limitation, that we must place on X and Y. They must be small enough so that this works. Right. Now, notice that you can take this equation and simplify. You can divide everything by 500, and it works out to 5x plus y is less than or equal to 100. So it's a lot simpler to work with this one. You could work with the original, but then it's a little bit more clunky. So this is the constraint for price. Right? Now what about this constraint for storage? Well, that's a little bit easier to come by. You can't have more than 60 pieces of furniture. So X tables plus Y chairs has to be less than or equal to 60. All right? So far we have 4 constraints: non-negative constraints on X and Y, investment constraint on X and Y, and storage constraint on X and Y. Now that tells us what we can't do. Now we want to know what we can do. What we can do is get money, and the amount of money that we'll get depends on the number of tables and chairs. 250 is the profit per table, 75 is the profit per chair. So my total profit is going to be 250 times X, which is number of tables, plus 75 times Y, which is number of chairs. So we actually now have completely characterized our problem. We want to maximize this quantity, which we call an objective function, and we have these 4 constraints. Now look at the mathematical form of the constraints and the objective function. They all look rather similar. In fact, if you think about algebra, these look like the equations of lines in 2 dimensions. Y equals mx plus b. I could take y equals mx plus b and rearrange to make it look like this. So all of these have this kind of form. These types of expressions are called linear expressions. So here we have all linear expressions. So all of these expressions here, they all are sums of terms, and each term is a constant times the variable. Okay, not a variable squared, or not one variable divided by another variable, but each term is was one constant times one variable. Okay, so this is actually called a linear combination. It's combination because you're taking the sum and you're multiplying also. So it's called a linear combination of variables. Okay, so a linear programming problem means that the objective function and the constraints are linear combinations of the variables. Okay, so that's how you can recognize a linear programming problem. So to reinforce this terminology, we have a linear function which is the objective function, and it can involve several variables, and it's subject to conditions that the variables are non-negative and satisfy linear inequalities, which are linear constraints. Okay, so I explained what the term linear means. So just as a review, objective function was what I want to maximize, and typically you write that as some other variable z. You want z to be as large as possible, so you want to find x and y values that get your largest possible z. The y and the x are your strategy variables, which we call decision variables, and I already talked about constraints. So we say optimization problem because sometimes in some problems you want to maximize, in some problems you want to minimize. In all problems you want to find the best solution, best or optimal solution. All right, so that's the terminology, and we'll stop there.